Motion in one dimension. Everything in the universe is in motion. The birds, the cars, everything is moving around us. Still, some things like chairs, tables, etc. are said to be at rest. So, what is the exact meaning of motion and rest? A body is said to be at rest if it does not change its position with respect to its immediate surroundings, while a body is said to be in motion if it changes its positions with respect to its immediate surroundings. The quantities related to motion that can be measured are called physical quantities, which are further divided into scalars and vectors. Visualizing the difference between the both, we can say that scalar quantities are the ones which are expressed only by their magnitude, whereas the vector quantities are the ones which are expressed by their magnitude and direction. For example, mass, length, all these are scalar quantities, whereas velocity, force, these are the vector quantities. Motion in one dimension? What's that? To answer that question, we need to know about the dimensions. So, there are three dimensions which are represented by three axes. We have x-axis, we have y-axis and z-axis. When a body moves only in a straight line, that is, only in a single axis, the motion is said to be in a single dimension. Some examples for rectilinear motion are a stone falling down vertically or a car moving along a straight road. Similarly, if a body moves in two or three axes, the motion is said to be two-dimensional or three-dimensional respectively. For example, a body moving in a curved path is said to be two-dimensional. Let us know about some terms before moving further about motion in one variable. So, look at this bus. It travels from point A to point B. The path is not straight, so it's a two-dimensional motion. This red line, as you can see, it represents the distance traveled by the bus. So, we can define distance that is represented by S as follows. Distance is the length of the path traversed by the object in a certain time. So, the distance travelled by the bus is 10 meters. This blue line represents the displacement of the bus. Displacement is represented by S with an arrow on top as it is a vector quantity, and it can be defined as the shortest distance between the initial and the final position of the body in a certain direction. So, the displacement of the body is 5 meters towards east. If the bus had returned to its starting point, the distance would have been 20 meters, but the displacement would have been 0 meters. The distance and displacement can be expressed in kilometer, meter or centimeter. Speed. A scalar quantity represented by v is defined as the rate of change of distance with time, whereas velocity, a vector quantity represented by v with an arrow, is the displacement per second by the body in a specific direction. Speed and velocity are expressed in kilometer per hour and meter per second. Let us look back into the same example where we calculated the distance and displacement, but now the time will also be considered. The bus travelled a distance of 10 meters in 5 seconds. By the definition of speed, speed is equals to distance upon time, or v is equals to s upon t. So, in this case, speed would be 10 upon 5, that is 2 meters per second. By the definition of velocity, velocity is equals to displacement upon time, or v is equals to s upon t. So, the velocity would be 5 upon 5, that is 1 meter per second. Here, the time would be obviously same, but the displacement would be as calculated, that is 5 meters. Now, let us hop into acceleration and retardation. Acceleration is represented by A with an arrow pointing towards right, and retardation is represented by A with an arrow pointing towards left. Both of them are related, as acceleration is the rate of increase of velocity with time and retardation is the rate of decrease of velocity with time. After knowing about all the important terms, let us study the rectilinear motion through graph. Displacement time graph or the ST graph, velocity time graph or the VT graph, acceleration time graph or the AT graph. A displacement time graph shows the displacement of a body on the y-axis and the time on x-axis. It is used to calculate the velocity of a body through its slope. Looking into some different cases now. The graph before you shows a straight line indicating that the displacement does not change with time and so the body is at rest. The next one shows the body covering equal distances in equal intervals of time, thus representing uniform velocity. Velocity is the slope or the gradient of the graph, that is, the perpendicular upon the base. With a curved slope, it would have represented non-uniform motion or non-uniform velocity. A velocity time graph represents velocity on its y-axis and time on the x-axis and is used to calculate the acceleration or the distance travelled by an object. The slope shows the acceleration or retardation and the area under the graph shows the distance travelled by the body. There are several situations depending upon the graph. This graph shows a body moving with constant velocity without any acceleration. The next one shows that the velocity of the body is increasing at an equal rate. That is, the body is uniformly accelerating. The acceleration here is the gradient, that is perpendicular upon the base, and the distance is the area under the graph, that is the area of the triangle. Had the graph been like this, it would have been the case of retardation, but with the same values. In a case where the initial velocity is not zero, the acceleration is shown as the slope, that is, this perpendicular upon this particular base, and the distance travelled by the body would have been the area of this trapezium. Visualizing the acceleration time or AT graph. We see that the acceleration is on its y-axis and the time on x-axis. It represents the acceleration or retardation with respect to time. If the graph has a straight line coinciding with the time axis, the body is either at rest or at a uniform velocity. If the acceleration is constant, the graph would be a line parallel to the time axis, and similarly, if the retardation is constant, the line would be parallel, but the line would be on the negative side of the acceleration axis. In case of non-uniform acceleration, the graph would be of any shape. Some important equations have been derived pertaining to motion in one variable. They are for uniformly accelerated motion only. The three equations are as follows. First is the velocity time equation, which derives that the final velocity is equal to the initial velocity plus acceleration into time. Next is the position time equation, which derives that distance is equals to initial velocity into time plus half into acceleration into time squared. The last equation is the velocity position equation that states that final velocity squared minus initial velocity squared is equals to 2 into acceleration into distance.